Hey, this is Dr. B yet again here, and let's have a look at some dyspeptics. These are medicinal treatments for dyspepsia, which is characterized by indigestion and heartburn. So we're going to be looking basically at stomach treatments. Your stomach maintains a pH that's very low, 1 to 2. It does so by adjusting the concentration of something that seems like it has no business being in your body, which is hydrochloric acid, which is one of 6 common very strong acids. And the gastric glands are modulated to adjust this concentration to keep it at that level. And so that's a point of treatment if you need to adjust the pH of a stomach. And typically dyspepsia is characterized by the gases entering your esophagus and leading to discomfort here. You can treat this directly with Tums, right, which is just simply calcium carbonate. That should reduce that. That should raise the pH, reduce the acidity. Or you can do it by a more sophisticated method. You could adjust the gastric gland activity. This can be done through the histamine receptor antagonist, and Zantac does that, so that's a pretty fancy way to do it. Or you can come up with a proton pump inhibitors. I'm not going to go into detail on either of these. I'll just show the structures of Zantac and Prilosec here. Yes, it looks like their molecular weight is well under 500. Yes, I do see a little bit of water solubility here and perhaps here, and these must bind to those receptor sites effectively. Now, some of these dyspeptics can be buffered, which means they'll resist a change in pH. Your stomach having a strong acid is not part of a buffer system, but let's use this as an excuse, if you will, as an entry into the field of buffers. There's 2 components in a buffer system, either a weak acid and its conjugate base, or the reverse, a weak base and its conjugate acid. Weak means it doesn't dissociate much. Example would be acetic acid, which only dissociates perhaps 1 part in 10,000. However, a 1 molar solution would be pH about 2.4. Its conjugate base means it has now formed the sodium salt. Notice the H plus is gone. It's not an acid, and in fact it would react with water to make hydroxide, so it is therefore a Bronsted base, and its pH does check in at 9.4. Now the best way to make something that will resist a change in pH would be to have an acid and a base in the same solution, and normally, great idea, but impossible, the acid will react to the base to make a salt and water. An exception to that are the weak acids and weak bases because they exist in equilibrium with their conjugates. So that just means if you have some acetic acid, it naturally will react with water to make a little bit of sodium acetate or some form of acetate, the acetate anion, right? And its acidic counterpart, H+. This means that you can have both this, which has a pH, as we've seen, of 9 if it's a 1 molar solution, and this, which is an acid, in solution at the same time. So it's kind of cute, isn't it? It's a way to have them both present simultaneously. And you can up the concentration of this. I mean, after all, it's very low naturally, and make a more potent buffer. Without going into the math behind it, there's a very handy equation that allows us to calculate the pH of a buffer system, and here it is directly. If you're dealing with an acid, for example, that's dissociating into a real acid, H+, that after all is what an acid is, and its conjugate, the pH is simply the pKa of that acid, which is simply a number that shows you the negative log of its Ka. The Ka is a measure of how much it dissociates, plus the log of each of these concentrations, where these square brackets mean moles per liter. Let's apply this to our 1 molar buffer system here. It's 1 molar in acetic acid. It's also got 1 mole per liter of sodium acetate. What will its pH be? Let's just plug in directly. There's the Ka, which is, by the way, that's where I got the 1 part in 10,000 roughly from. It's a very low number. All the weak acids are. And pKa means take the negative log of that, which will be 4.76. And you add to that the log of these concentrations, but hey, they're the same. So it's the log of 0, which is log of 1, I believe, which is 0. There it is. and you end up with a pH of 4.76. That's a little bit about buffer systems and how you can calculate their pH.